Hey everybody, welcome back. We're going to continue with our logarithms chapter. Now, in this section, we're dealing strictly with exponential equations. So those are equations, right? The equation means there's going to be an equal sign in between, where we start with exponents. And how do we solve them? No logarithms yet. We can use logarithms to solve them, but we'll get to that shortly. And just a quick overview. Remember what exponential equations are. It's y is equal to a to the power of x. That's in exponential form. I can write that exact same equation in logarithm form. And logarithm form is the exponent is equal to the logarithm of base a, right? Little subscript on the word log with the argument y. So those two equations are exactly the same. One's written in exponential form, that's the one on the left, and one of them is written in logarithm form, that's the one that's on the right. So in this section, it says, you will notice as we solve these exponential and log functions that there are multiple ways to find your answer. So often you get creative with solving the unknowns. We'll look at some common ways in this section. So just like when you solved a quadratic, for example, you could find the solutions by factoring it to find the x values. You could use completing the square. You could use quadratic formula, lots of different ways to get to your answer. So there's not only one way that you can get to your answer. So I'm going to show you a couple different ways here. So first one says, solve the exponential equations is all about getting a common base and equating the exponent. So basically it's saying, get a common base on the left side and the right side. And if you have that, that means the exponents must be equal to each other. So for example, this first one here, we have 3x is equal to 81. So the one on the left has a base of 3. So I want to write 81 as a base of 3. So maybe you look at yourself and say, well, I know that 3 to the power of 1 is 3. 3 to the power of 2 is 9. 3 to the power of 3 is 27. 3 to the power of 4 is 81. So we rewrote 81 as an exponent with base 3. So from there, I know that the exponents must be the same. X must be equal to 4 because they're in the same location on the left and right side. We equated them. They're equal to each other with that same base. All right, next one. It says 10 times 3x, 3 to the power of x, is equal to 2,430. So we want to know what the x value is that would make both sides balance. So 10 bracket 3 means it's 10 times 3. So in order to get rid of that one, I'm going to divide both sides by 10, first of all. That's going to leave me with 3x is equal to 243. So from there, you might say, well, how do I get x by itself? Well, I'm going to get common bases. 3 is the base on the left side. So I want to say, well, what is the base of 3 that if I put an exponent on it will give me 243? So you might try your calculator, or maybe you know that 3 to the power of 5, right? You can use trial and error, but 3 to the power of 5 gives me 243. So if I look at that, the left and right side both have the same base. The left side has an exponent of x. The right side has an exponent of 5, so x must be equal to 5. All right, keep rolling along here. Third one has an exponential on the left side and on the right side. So if I want to solve that one, I look at this and say, well, 9 to the power of x plus 1 is equal to 27 to the power of 2x minus 3. So they do not have the same base. But one thing I know about 9 and 23, I can write them as the same base of 3. So for example, that 9, I can write that as 3 squared. All of that to the power of x plus 1. So all I did was change that base of 9. It's really 3 squared. Same with 27. I'm going to make it 3 to the power of 3, 2x minus 3. Leave that exponent. So you might say, how do I work with this now? Well, one thing you might remember from grade 9 was when you had a base raised to an exponent raised to another exponent, you could multiply these powers together. It's called the power of a power rule. Right, I'm going to have to distribute that 2 into both of those values. That's going to leave me on the left side with 3. Well, 2 times x is 2x, and 2 times 1 is 2. On the right side, same idea, base of 3, and I'm going to distribute 3 into that binomial, right? Power of a power rule. 3 times 2 is 6x. And 3 times 3, negative 9. So now I look at the left and right side. Both have the same base of 3, so those exponents must be equal to each other. Right? I must have 2x plus 2 has to be equal to 6x minus 9. And now I'm going to isolate. I'm going to bring 6x to the left side. So I'm subtracting 6x will give me negative 4x. Right? Because 2x minus 6x is negative 4x. On the right side, negative 9. Take away 2, because that 2 is going to come over to the right side. It's going to become negative 11. Right? Kind of did that quickly here. Right? Really, we're subtracting 6x from this side and from this side. And then I'm subtracting 2 from this side and subtracting 2 from that side, if you're not sure. Basically, we're just isolating x. Next, I want to divide both sides by negative 4. So that's going to give me x is equal to 11 over 4. Right, both are negative. That's why it becomes positive. And that's that one. Or you can get 2.75 if you put it as a decimal. But that's the third one. All right, keep going along here. This one's a little bit different. So sometimes we can factor out a base and an exponent. You might say, what the heck does that mean? Well, if we have this expression here, where on the left side I have two terms and both of them have a base of 3, I can factor that out. I can factor out 3 to the power of x. Actually, I'm going to leave a little bit more room here and put a little bit lower here, just to show you what's happening. So remember, when we're factoring, we're really dividing each of these by 3x, right? So like, just a quick example here. If I had 2x plus 6 and I factor out 2, well, 2 goes out front, and then I divide each of these by 2 and I get x plus 3. Well, I'm going to do the same thing. I'm factoring out 3 to the power of x, so I'm dividing each of those terms by 3 to the power of x. So one thing that you might remember, when I'm dividing two powers with the same base, so they both have a base of 3, when we divide two powers of the same base, I keep the base the same, and I subtract their exponents. So it's going to be x plus 2 minus x. X plus 2 minus x. Well, that's x minus x. That's just 2. And next one, we have 3 to the, you might look at it and say, well, I'm dividing the same term on the top and bottom, so I know it's going to be 1. But suppose you didn't see that, you would have 3 to the power of x on top, subtract x, right? Because we're dividing two powers to the same base of 3. So x take away x is just 0. And you might remember that anything raised to the power of 0 is 1. Now we look at this and say, okay, well, that doesn't look any easier, but I can simplify inside that bracket now. 3 squared is 9. And 9 take away 1 is 8, so I get 3x times 8 is equal to 216. And now I can divide both sides by 8. I can take that 8 out. Divide this side by 8 and divide this side by 8. I will get 3x is equal to 216 divided by 8. So when we put in our calculator, we get 27. And then it's just like the ones that we saw above. We want to get the same base on both sides. So 3 to the power of x is equal to, well, 3 to the power of what gives me 27? 3 to the power of 3 gives me 27. So x must be equal to 3. Those exponents are equal because they have the same base. So that's one method, getting this common base on the left and right side and making those exponents equal to each other. We'll keep going here. It says, when we cannot get a common base of each side. So a lot of those ones worked out to be a base of 3. But what happens if we cannot get them? Right? It's not a nice whole number. It is often easier to take the common logarithm, right? Log base 10 of both sides and apply the power law. Remember what the power law was? That was if we have something like log of anything, log 5, for example, x to the power of 3. Well, the power law said, well, this 3 really can come out front and multiply it. So it becomes like 3 times log 5 of x. if there's an exponent on it. So you'll see us apply that rule here. So solve each equation by taking the common logarithm of both sides of the equation and solve them. Sounds easy enough. So this one here, we have 2x is equal to 9. I wonder what exponent we can put on 2 that will give me 9. Right? It's not a nice whole number because I know 2 to the power of 1 leads to 2. 2 to the power of 2 leads to 4. 2 to the power of 3 leads to 8. And 2 to the power of, did I say 4? 2 to the power of 4 works out to be 16. So I know that it's going to be somewhere between 3 and 4. A little bit closer to 3 than 4, but I don't know exactly because it's not going to be a nice whole number. So what we can do is we can take the logarithm of both sides, log this side and log this side. We're taking the common log, so that means they're both going to have base 10. So if I don't put that 10 there, it's assumed that it's going to be 10. So I'm going to do that here. Log, I'm going to write it here, 10, 2 of x is equal to log 10, 9. I don't need that 10 there, but that's just to show you that we're taking the common log, which is base 10. Whoops, I erased the g's on both of them. So you don't have to put that base 10, but when there's nothing there, you assume it's 10. So we look at this and say, okay, well, now I'm trying to solve what we've got here. Well, on the left side, I have log 2 to the power of x. Well, remember that rule says that this x can come out front. So x times log 2 is equal to log 9. Now, if I want to get x by itself, well, x is being multiplied by log 2, so I'm going to divide it by log 2. I have to do that to both sides. That leaves me with x is equal to log 9 divided by log 2, and that's where we can use our calculator. That's why we took the common log of both. So when I put in my calculator log 9 divided by log 2, we get a number of 3.17 about. Right, we said it was going to be between 3 and 4. We said it's going to be a little bit closer to 3. Didn't know exactly what it was going to be. Now we know it's about 3.17. It's 3.16992. But that's that one. All right, let's keep rolling along here. 6 to the power of t plus 1 is equal to 8.35. So I can't get common base on both sides. I don't know what 6 to the power of what would give me 8.35. So what we're going to do is take the log of both sides. So I'm going to have log of 6 to the power of t plus 1 is equal to log of 8.35, right? Those both have base 10, those logs. And then we're going to apply that power rule. So the t plus 1, well, that's going to come out front. So it's going to be t plus 1 times log 6 is equal to, right side's going to stay the same. Now here I have a couple options. Probably the easiest, if we look at where t is, I want that by itself. I see that bracket is being multiplied by log 6, so why not just divide out log 6 right away? Right, that'll get rid of it. I could have distributed inside t times log 6, 1 times log 6. Done that as well if we wanted to. But it's probably easier just to divide by log 6 right here. So that's going to leave us on the left side with t plus 1. On the right side, that's where we need our calculator. We get log 8.35. And we divide that by log of 6. And we get 1.18 about. And now I want t by itself, so I'm going to have to subtract t from 1 from both sides. So t is going to be equal to 0.18 when I subtract 1 to both sides. And that's the answer. You can always make sure you got it properly by putting it back into the original equation and see if you get left and right side to balance, and they will. But always you can check. All right. What's happening with these ones? So, next one has 3 to the power of x plus 1 is equal to 4 to the power of x. I can't get common bases, right? I have 3 and I have 4. Not an easy way to do that. So I'm going to take the common log of both sides. We're going to have log of 3 to the power of x plus 1 is equal to log of 4 to the power of x. Now in this case, I'm going to apply that power rule to both sides. That x plus 1 is going to come out front. The x is going to come out front. So that's going to leave us with x plus 1 log 3 is equal to x log 4. So now at this point, I have x's on both sides. So I'm going to have to bring all the x's to one side. So I'm going to have to, on the left side, distribute log 3 into that bracket. I'm going to get x log 3, wait, that's log 3 times x, plus 1 times log 3, which is just log 3, is equal to x log 4. So from here, I need to get all my x's onto the same side. So I'm going to take x log 4 and bring it over to the left side. Right, they're connected, right? They're multiplication. It's like, you know, log 4 is just a number. It's like 2x. Right, they're together. So when I bring that over to the left side, I'm going to have to subtract it. I'm going to leave x log 3 over here, or x times log 3 over here. Subtract x log 4 is equal to, well, I'm going to bring log 3 over to the right side, so it's going to become negative log 3. Keep in mind that log 3, log 4s are just numbers. Now on the left side, I have an x in both terms, so I'm going to factor it out. Common factor it out. And right side's going to stay the same. And now I have x times that bracket. I want x by itself, so I'm going to divide both sides by that bracket. Log 3 minus log 4. I'm going to do that to both sides. Log 3 minus log 4. So that leaves with just x on the left side because these canceled out. So I'm going to have to put these into my calculator. You got to make sure that we put that in properly. If your calculator has memory, you might need to add brackets to the log 3 minus log 4. But what I do is in my calculator, I put it the top first. So I say negative log 3 and I get an answer for it. Hit equal. You should have negative 0.47712 continuous number. But you should have that in your calculator for just the top. And then I hit divide, and my calculator says the answer divided by, and if I just put log 3 minus log 4, it doesn't know what to divide by, whether it's just the log 3 or both. So that's why I open up a bracket in my calculator, and I say, what's on the denominator? Well, the bracket is log 3 take away log 4. So I know that all of that's on the bottom. We should get the number 3.82, about 3.818841679, right? Continuous number, but I rounded it there. So that's our x value. So that was a little bit different because we had a common factor out that x because there was an x on both sides. Don't be confused by log 3, log 4. They're just numbers, right? If I put those into my calculator, it would just give me some decimal. So don't be confused by all the words that show up. All right, let's keep going here. Next one, we have base 2 and base 3. 2 to the power of x plus 1 and 3 to the power of x minus 1. So I can't get common bases, so once again, we're going to take the common logs. This is going to be very similar to the one that we saw before. So log 2 x plus 1 is equal to log 3 x minus 1. Keep in mind, those are base 10. We didn't write anything there, and when nothing's there on the log, it's assumed that there's a small 10 on them. So that being said, this exponent on both is going to come out front. That's that power rule. So I'm going to have x plus 1 log 2 is equal to x minus 1 log 3. So I'm going to have to distribute in both brackets, and then I'm going to have to bring all the x's to one side and the non-x's to the other side. So when I distribute inside, I should get x log 2 plus 1 times log 2 is log 2. Right, just distribute it on the left side. I'm going to distribute log 3 into that bracket on the right side. we get x log 3 minus log 3. So now I have to get all the like terms on the same side. So I identify where the x's are. There's one here and one here. So all right, bring it all to the one side. So when I do that, I have x log 2 minus x log 3 is equal to, well, on the right side, I'm going to have negative log 3, because that was already there. And it's being joined by log 2. So log 2 is coming to the right side, so I have to subtract it. So that's all together. Doesn't need to be in a bracket, but it's all together. Now on the right side, I'm going to common factor out that x like we did earlier. So when I common factor out, I get x log 2 minus log 3. Just took that x out from both those terms. Right side's still going to stay the same. And finally, just divide both sides by whatever's with x. In this case, log 2 minus log 3. Divide both sides by log 2 minus log 3. Log 2 minus log 3. That leaves us with just x on the left side. And then on the right side, once again, you got to make sure you put those into your calculator properly. You might need to have an entire bracket for the top. So like negative, open up bracket, negative log 3 minus log 2. So that's everything that's on top. You should have a number of negative 0.778 for the top. I'm going to divide that by, and then open up a bracket for the bottom. Each calculator is different, so you got to know how to use yours. But on the bottom, I'm going to put log 2 minus log 3. And end that bracket, and we get 4.42 when we round it. Right, it was 4.4190, so we round that one to 4.42. And as always, you can always test your answers. Put it back into the original equation up at the top for x and see if the left and right side balance. They should be pretty close because we rounded it ever so slightly. They might not give you the exact same number on the left and right side, but it should be very, very close because we rounded it and we rounded to nearest hundredth. So the more decimal places you keep, the better. But in this case, we kept 2. All right, we'll look at a couple of word problems, some applications of them. Now, these rely on some formulas that you learned back in grade 11, but I'll go through them pretty quickly here. There's a compound interest formula, which is the top one here. And what that is, it means basically used with money as money grows, where A is the amount in the future, AO is the amount you started with, A at time 0, so at the very beginning, what you began with, called the principal amount. Inside the bracket, we had the interest rate for the entire year. That's R. And N is the number of compounding periods per year. That means how many times you reinvest the money throughout the year. So if it's like quarterly, that's a 4. If it's monthly, that's 12. If it's weekly, that's 52. And then up at the top, N, well, that's already, we talked about that. That's how many times it's compounded. And T, that's the amount of years that the money's been invested. So let's look at the first one here. How long does it take $250 to double? So that means become 500. If it's invested in an account that pays 12% per year, compounded quarterly. Okay, so let's go through our formula. Our A, our amount in the future. Well, it wants to double. That should be $500. AO, the amount that we started with. Well, we started with 250, it says. Next, it says R, the interest rate for the year. So it says 12% per year. So that's 12%, but we know we write that as 0.12. And N is the number of compounding periods. So it says quarterly, so that's 4 times a year. We reinvest our money. It's like once every 3 months, basically, 4 times a year. And then finally, T is what we're trying to find out. T is what we don't know. It says how long was it invested for? So how many years? So let's put that all into the formula. So that's the top formula. A is equal to 250, 1 plus 0.12 divided by 4, all to the power of 4t. So I'm trying to isolate for that exponent that we have up top. So what we're going to do is, first of all, I have 250 times that bracket squared, bracket to the power of 4t. So I'm going to divide both sides by 250. So when I do that, divide this by 250, divide this by 250, we get 2 is equal to the bracket 1 plus 0.12 divided by 4 to the power of 4t. So I'm going to simplify it here a little bit, but we're just dividing both sides by 250. And then inside the bracket, I can divide that, right? 0.12 divided by 4, just to simplify it. When I divide those, I get 0.03. So, and when I add that to 1, so 1 plus 0.03 is 1.03. So now I have one of those exponential equations. I cannot get the same base on both sides. I have a base of 2 and I have a base of 1.03. So in this case, I'm going to have to take that common log of both sides. So I'm going to have log 2 is equal to log of 1.03 to the power of 4t. So I use that power, that 4t comes out front. 4t times log 1.03. And divide both sides by log 1.03 because I want t by itself. So that gives me 4t is equal to log 2 divided by log 1.03. And I'm going to have to divide by 4 as well. So that's going to be, you can solve the log part there first as well, but it's really going to be divided by 4 as well because I'm going to have to divide both sides by 4. So essentially we get t is equal to log 2 over 4 times log 1.03. Right, that dot is multiply. So I put that in the calculator, find out how many years we're talking about. So log 2, get an answer for the top, divide it by, maybe I have to open up a bracket depending on the calculator, but 4 times log 1.03, that's all the denominator. So you might have to experiment with some brackets to solve these, but essentially you should get t is equal to 5.86. So what is that? Well, that's 5 years and 0.86 of a year. How do I find out what 0.86 of a year? Well, I can put that in my calculator. 0.86 times 12. Find out how many months that is. That's 10.32 months. Right, so just 5.86 years basically the question is, but we broke it down to even further to 5 years, and 0.86 of a year is 10 months, or a little bit more than 10 months. And that's that one. So we know how long it will take that money to double. All right, next one. A bacteria culture doubles every 15 minutes. How long will it take for the culture to, for a culture of 20 bacteria to grow to a population of 163,840? So we have two formulas for this to simplify. We have half-life and double. Half-life means how long it takes something to half itself. So that happens a lot with radioactive material. They hang around for a long time because they have a long half-life, because things break down over time. So if I have, like, I don't know, let's say there was a banana in, I was eating a banana and I threw it in the corner and there was 100 grams of the banana. After time, I want to know how long it would be until it decays down to 50 grams of what it was. That's a half-life time. So if it took 5 days to decay in the corner, and now there's only 50 grams of, a brown banana, its half-life time would be 5 days. So same goes for doubling, how long it takes something to double, right? Usually population, things like that, have a double time. So that's the double life formula. So A is the amount in the future. AO is the amount at time 0, which is the beginning. 2 is 2, right? We're doubling. And T, once again, is the amount of time in years. And D is the doubling time, how long it takes to double. So let's fill in all of our information that we know. A, I know the amount in the future. Well, it told me it was 163,840. AO, that's how much we started with. It was a culture of 20 bacteria. But T is the amount of time. I don't know what that is. It says how long does it take? And then finally, the doubling time. I know that it doubles every 15 minutes. So when I get my time, it's not going to be in years because D is in minutes, so it's going to be in minutes as well, so the amount of time it takes. So let's go through, let's plug it all into that double life formula. So we have 163,840, right? That's A, is equal to 20, 2 to the power of T divided by D, which is 15 minutes. So you should be looking at this one here and say, well, it's kind of like the one from before. I'm just going to divide both sides by 20 because that's going to give me just the base, just the exponent part, the base and the exponent together. So when I divide those ones, divide both sides by 20, I get 8,192 is equal to 2 T divided by 15. Then from there, you might say, well, I'm going to try to get the base of 2 on both sides. See if I can get that to match. So you could be here all day, 2 to the power of 10, see if you'll ever get that one. 2 to the power of 11, and keep going. 2 to the power of 14, too high. 2 to the power of 13 is equal to 2 to the power of T over 15. So that means I know that 13 must be equal to T over 15, right? We equated those exponents. Now, in order to get T by itself, I can multiply both sides by 15 because T is being divided by 15. 13 times 15, 195 minutes. And that's how long it takes for that bacteria, which doubles every 15 minutes, to start at 20 and end up at 163,840. Now you might have said, well, how the heck did you know that 2 to the power of 13 or 2 could be a nice base of 8192? Well, because I did it before. If you did not do it before, what could I have done? Well, we could do the same thing that we did before. Take the common log of both sides. I could have done, I'm going to show you this one here too. 8192 is equal to 2, whoops, I'm logging that side as well. Log of 2 T over 15. Now that T over 15 is going to come up front, so I'm going to have a log of 8192 is equal to T over 15 log 2. And I want T by itself, so there's a couple different ways, but the first thing you can do is multiply both sides by 15. Because that's going to erase it off the bottom. So I'm going to have 15 times log 8192 is equal to T times log 2. All right, multiply both sides by 15. When I multiply the right side by 15, this 15 was gone. Now it's on the left side. Then finally, T times log 2. I'm going to divide both sides by log 2. I get T is equal to 15 times log 8192 divided by log 2. Right, when I divide by log 2, it's gone from the right side. Then when I put that into my calculator, I get 195 minutes. So it did not matter. Finding the common exponent was a little bit faster because I did not need a common base because I didn't have to go through the logs and isolating. But both ways will give you the exact same answer. It doesn't matter how you get there. And that's this section here where all the equations started out as exponents and you can solve them like so, using either common bases on both sides and set the exponents to equal to each other, or take the common logarithm of both sides. That's log 10 of both sides. Both work out fine. If you have any questions, be sure to let me know. But I know it's a little bit difficult at first, but with practice, you'll be just fine. Don't worry. There's some practice questions in your textbook at the bottom here, and we'll talk to you soon.